Okay, here is our question. We have to design a safety system to protect drivers going down hills during an ice storm. Let's start off by drawing an image, a picture. So we have a hill, and at the bottom we have a spring. Cars start at the top of the hill and then move down, getting faster and faster until they hit the spring. And then the spring shrinks. It moves from its equilibrium position a distance d. What else do we know? We know that the slope has an angle of q to the horizontal, and the distance that the car slides from the top of the hill until it is stopped by the spring is L. Okay, what method should we use? Nothing is rotating, so we don't need the angular momentum method. We could do it by using forces. We could look at the components of the forces on the car. So there's a downward gravitational force and a normal force like that, and use those to work out its acceleration, and therefore work out how fast it accelerates and how fast it's moving here, v. But once it hits, it will become more complicated. The spring will push back, and to begin with it will push back without much force, and as the spring gets more and more compressed the force will get bigger and bigger. So working out the acceleration downwards would be pretty easy. It would just be accelerating at a constant acceleration, but the slowing down would be much harder because the acceleration is changing. So force, tricky. How about energy? All we really care about is going from this state up here to down here with everything compressed. No energy is going to squashing anything or a sound, so none is being lost. And there are no outside forces acting on the system, so energy looks sensible. What sorts of energy are going on here? We have gravitational potential energy at the beginning. So the potential energy is mgh. H would be the height here. M the mass, and g is the gravitational constant. So at the beginning it's not moving, so there's no kinetic energy. The spring is not moved away from its equilibrium position, so there is no spring energy. So that's all we have at the beginning. How about at the end? At the end it's moved all the way down, so at end PE, potential energy, is 0. The kinetic energy is 0, because when the spring is its maximum compression, the car has come to a rest temporarily. The only energy we have is spring energy. And the equation for spring energy is 1/2 k d squared, which you can look up. So we know that the starting energy is mgh, the end energy is 1/2 k d squared. As energy is conserved and none is being lost, no work is being done on the system. It just means that mgh equals 1/2 k d squared. But what is h? Remember we had a slope of length L, angle Q, and H is here. So using trigonometry, opposite over hypotenuse is sine, so sine Q equals opposite H over hypotenuse L, which means rearranging that H equals L sine Q. Substituting this back into here, we have mg L sine Q equals half k d squared. What do we want to know? We want to know d. The question asks us, we want to know k. If we look at the question, it says your job is to calculate the required spring constant k in terms of d, L and q. And here we have an equation which has k in it, also d, L, q, the mass and gravities. More things we might know. So let's rearrange it to make k the subject. Multiply both sides by 2 and divide by d squared to get rid of the half and the d squared. So that means 2mg L sine q over d squared equals k. And that's our answer. Let's check for plausibility. One way to check is to see what the equation does in limiting cases. Does it behave in the right way? So let's see. If the mass of the car was bigger, well, you're going to need a stiffer spring. Does that work? If m is large, k is large. If you look, because k is proportional to m. So k proportional to m. So that works. You would also expect k to be bigger if the slope was longer, because the car will be sliding faster when it hits. And sure enough, k is proportional to L. Likewise, if gravity is stronger, k will be bigger. So, similar for GL, also Q. If the slope is bigger, it should slide faster, and indeed sine Q goes up as Q goes up, so that makes sense. However, if D goes up, K goes down. That means if the spring compresses more, you need less spring constant. So if that makes sense, D goes down, K goes up. All makes sense. So a plausible equation. Doesn't mean it's right, but it's at least plausible. So in this case, it is right.